So the one algorithm that many people have heard about, of course, is Shor's algorithm. Shor's algorithm is a way to factor large numbers and can be used for cryptanalysis. But, to the best of our knowledge, that's a good 20 or 30 years off. And even so, cryptanalysis, there are a few governments in the world that may want to use that, but that's not the real commercial driver. And what we think is going to be the commercial driver are applications such as optimization and quantum simulation. These are the killer apps that we think are going to be commercialized within the next 5, 10, 15 years. If we talk about near-term applications of quantum technologies, of course, perhaps the nearest term application is in the field of quantum sensing. And this includes magnetic field sensors or precision timekeeping, precision measurements of gravity. So for example, magnetic field sensors can be used to image what is happening below ground. So for example, petroleum companies currently use squids to see, to scan over an area of land and find out where, potentially petroleum deposits are located. This is one application of quantum sensors or sensitive magnetometers. Another is precision timekeeping. So for example, we have server farms that are set up, and these server farms can service, many large numbers of clients. Of course, they're all running at gigahertz frequencies, and so if you have millions of people using it and nanoseconds matter, then you have to keep track of who's, accessing what data and changing what data. You might have two people coming in almost concurrently. You have to keep track of that. And so one of the biggest motivations for making precision timekeeping is actually these large server farms that are being set up today. So another application is navigation in GPS-denied environments. If you lose your connection to, say, a satellite, can I use quantum sensors to maintain my position and plot my course? And the answer is that yes, you can do that with quantum sensors. One of the near-term applications is quantum chemistry and simulating quantum systems and learning how those quantum systems behave. These are hard computational problems, and a great example of that is the nitrogen fixation problem. So, about 2% of energy use worldwide goes into the production of ammonia. And it's very important because ammonia, of course, goes into fertilizer, and we use fertilizer to feed, the people on Earth. But of course, 2% is a lot of energy usage, and in a world where we're concerned with climate change, we would like to find a more efficient way to produce ammonia. Now, the approach we use today is called the Bosch Process. It's developed in the teens, I think, 19 teens, so more than 100 years ago. And it's very energy inefficient. It uses high power, high temperatures, high pressures, to do this nitrogen fixation to make the ammonia. And yet, we know that there are bacteria that can do this with what their metabolism affords them. And so, of course, what it comes down to is a particular enzyme, a protein, a nitrogenase, but it's large enough that it's hard to simulate on a classical computer. Okay, so we do the best we can. We make approximations, and we use our classical computers to try to simulate it as best we can. But for some molecules, of course, that works, but for others, it doesn't. The answers we get out just lose fidelity because we've made too many approximations, and nitrogenase is one of those. If we could learn more about the reaction rates and how they occur, we might be able to figure out more efficient ways to produce ammonia and reduce the energy usage to do it. So nitrogenase is just one example, but it comes down to quantum simulation, and that's quantum simulation of materials, quantum simulation of quantum chemistry. Can we make a better material? Can we make a better drug? Can we reduce the energy usage in doing industrial processes? And these all come down to discovery of new materials, new processes, new pharmaceuticals.